Hi Calculus student, this video is for chapter 4.8 part 2 L'Hopital's rule for finding limits to infinity or limit as x approaches a. And in the last video, part 1, we talk about how if the ratio of two function has to be a ratio of two function, it ends up in infinity over infinity or 0 over 0, we would just take the derivative of the top and bottom and the limit would be the same. So in this particular one, we are tackling those where we see when we do a direct substitution, it's not a ratio of two function, but it becomes 0 times an infinity or 0 minus or infinity minus an infinity. So in this case, we can still apply L'Hopital's rule. This one is spelled wrong. But before we do that, we cannot just do them one by one. Just like here, this is x and x. We cannot do this one and this one. We have to write them as a ratio of two function and then make sure that it is 0 over 0 before we can apply the L'Hopital's rule. Is it actually, I think it has here. So like this is an example. Limit x approaches 0 from the positive side, from the right side, x, ln x. So if we do direct substitution, you would see that it is 0 times ln 0 from the positive side is negative infinity, right? So it's a 0 infinity case times infinity case. We would say that we can use L'Hopital rule if we can rewrite it. So we have to rewrite it as a ratio of two functions. So what's the best way? Best way would be maybe rewrite x as 1 over x. So I will rewrite it as limit still the same thing, but ln x stay at the top, and then 1 over x. You see how when you divide it by 1 over x, the same as times x, right? Now, when you do direct substitution, do you have infinity over infinity? It is, because 1 over 0 is infinity. So we can do L'Hopital rule. So that means I keep the same limit, so don't do it, but I'll take the derivative. ln x derivative is 1 over x. 1 over x derivative is negative 1 over x squared. So after you simplify, it is equal to 1 over x times negative x squared over 1. That is negative x. But x is approaching 0 from the positive side, so it's 0. So we end up it ends up that we can do it. But notice that we have to rewrite it. If you see some multiplying x, you automatically do 1 over x. Now, but this is a little different. We can do it another way. So we say x is approaching 0 and then it's called tan x. You still remember? So of course, when you do direct substitution, this would be 0. Cotangent's graph is what? From the period is from 0 to pi. And it's like that, right? So this is the cotangent graph. So if you approach from 0, I think from the positive side or negative side, so otherwise it doesn't work. So from the positive side, it's go to infinity. So we have to rewrite it. But did you see that cotangent is actually 1 over tangent? So I can write it this way. Instead of moving x below, I would just write x over tangent x. And then when I plug in 0 here, for tangent, it's actually better because tangent's graph is like that, right? When it approaches 0, it's actually 0. So it is a 0 over 0 case. I am going to do L'Hopital rule. So do the derivative of x. So limit x approaches 0. Limit of 1. And then this is secant square. Now I can do direct substitution is 1. Okay, 1 over secant 0 is 1. Secant is cosine. And then the other case is infinity minus infinity. Again, you have to rewrite it as f of x over g of x, and then get the 0 over 0 or infinity over infinity case. So let's say we have x approaches 0 plus 1 over x squared minus tangent x. So this is infinity. I don't know why I write that. Maybe I'll just erase this. So I'm supposed to plug in to check that it is infinity, subtract infinity. So 1 over 0 is infinity. Okay. Cotangent x, remember cotangent is this graph, right? So it's also infinity. So it is the case that we can do rewriting. So I will choose to rewrite it as x approaches 0 positive. 1 over x squared minus 1 over tangent x. And then I'm going to put it into, it's still not g of x, f of x over g of x. 0 plus. I'm just going to do common denominator to force it as two function. X squared tangent x, and then tangent x minus x squared. Why? Because you do common denominator. This one you multiply tangent x on both sides. This you multiply x squared and x squared on both sides. So you end up having this. Now when you do direct substitution, tangent is 0 over minus 0. And this is 0. So it is a indeterminate form. So I can do L'Hopital rule. But the terms are quite rather difficult. So in the top, you would have secant square x minus 2x. At the bottom is a product rule. So fig and jib. So it'll be 2x tangent x plus secant square x, right? You'd fix this, so it'll be x squared secant square x. Oh, it's still doing a limit. Okay, limit x approaches 0. So I'm going to do plug in. Secant square is 1, right? And then minus 0 over the bottom is all 0. So 1 over 0 is infinity. Whenever you have 1 over 0. The other one that you see that might be able to benefit from the L'Hopital rule is when you have the direct substituting result being 1 over infinity, infinity over 0, or 0 over 0 to the power 0. I should not say over. 1 to the power of infinity, infinity to the power 0, or 0, 0. Notice if it is infinity, infinity is just infinity, so there's no need to consider that case. So the way to do this is to take natural log for the derivative L and then find the limit as e to the L. Okay, so the first case is infinity to the 0 case, because when I do limit x approaches infinity, my base is infinity, but my 1 over x is 0. So this is the case where 1 is growing fast, but the exponent is just 0. So, but it's not 1. So the answer is not 1. So you would have to do L'Hopital rule by rewriting. So you would rewrite it as what? You would rewrite it as ln. Try to do ln limit x approaches infinity, x to the 1 over x. And because ln is continuous, you can switch them. Remember this you learned a long times ago? So it'll be ln x 1 over x. So you can move the limit outside. X approaches infinity, no, move the 1 over x outside of log the 1 over x, ln x. So this become a f of x, g of x situation. So you can check if L'Hopital rule can be applied. Still over infinity, approaches infinity, ln x over x. When x approaches infinity, of course ln x is infinity, and then this is infinity. So I can do L'Hopital rule. ln x 1 over x. Derivative of x is 1. So, but then limit is x approaches infinity. So 1 over infinity is 0. And that's the answer. One more case, 0 to the 0 case. Oh, no, that's not the answer. That's the ln 0. So what is our L? L is e to the 0. So this is ln of the limit. Okay, ln of the limit equal to 0. So L is e to the 0. I almost forgot. So this is the same. We have plug-in is equal to 0 over 0. So it is indeterminate form. But we have to rewrite it using ln. So we, instead of doing that one, we do limit ln of x to the sine x sin x can move outside, so it is as if you're doing x approach 0 sin x times ln x. So we need to rewrite it as f of x, g of x. So there is a number of ways to do it. The book, if you read the book, they would leave sin x in the top and move ln x as 1 over ln x. But I want to do it this way because I don't want to do 1 over ln x. I want to leave ln x in the top. Gosh. Oh, so did we check that it is a yeah, we rewrite it first. ln x in the top, and then the reciprocal of sine is cosecant, right? Cosecant x. So when you plug in 0, approaching 0 from the positive side, so this would be negative, it would be infinity. So, and then when you do 1 over, sine is 0, but 1 over 0, 1 over sine would be infinity. So it's infinity to infinity case. So we can actually do L'Hopital rule of this one. So this would become 1 over x. Still the same limit, x approaches 0. And cosecant would be cosecant x cotangent x. Okay. I don't know if you still remember. I think it's negative. Negative cosecant x cotangent x. And so we would need to make it so you have two things, top and bottom. So I can see that cotangent can move up as tangent x. Because I like the fact that tangent x eventually becomes secant, and secant is easy to get into 1 if you plug in x approach 0. And then the x would move down, and then we have cosecant x. Okay, so this would be this rewriting, and if you plug in 0 over 0 is 0 over 0. So we can do L'Hopital rule. I forgot my limit. I should write the limit. X approaches 0. So do derivative of this would be secant square x. Do derivative of this is product rule. So be x cosecant x cotangent x plus cosecant x. So when you plug in 0, you would have 1. Okay. When you plug in you plug in 0, yeah, you can have 1. And then when you plug in 0 here, whenever you do cosecants, that is infinity, right? So this is infinity. 1 over infinity is 0. Okay. Constant over infinity is 0. So that means that the limit is what? Is g to the 0 is equal to 1. So that's the limit. I get very confused when I have 1 over infinity. The rest of it is about growth rate. So sometimes we can also find limit by discussing that a particular function grow faster than some other function. It is discussed extensively in the book. The book actually had a very detailed description on this. They use graph. They actually calculate x to the cube to the e to the x. So which one grow faster? And it turns out that e to the x grow much faster than any polynomial x to the something. Even to the x to the 4, after a certain number, it will grow faster. And then they also compare how, square root x and ln x, or even cube root x, they grow much slower, but ln x grow much slower. So another way of doing limit is to compare the growth rate, and then I have the results here. Anything ln is grow less than all of these, the fastest growing index to the x. So if you do a limit of the two, one of them grow faster than the other, then like if the bottom grow faster, you have 0. If the top grow faster,